An interstellar comet glows red in X-ray light. 250,000 miles of ghostly halo. Carbon, nitrogen, oxygen signatures where none should be. This is 3I Atlas, third confirmed visitor from beyond our solar system. And on December 3rd, 2025, the European Space Agency's XMM-Newton observatory locked on for 20 straight hours. What it captured rewrites everything about how we track objects from alien star systems. Because when those gases collide with solar wind, they don't just glow, they scream in wavelengths we've never confirmed from an interstellar object before. Until now, we've only guessed. Now we have proof, and the data is stranger than anyone predicted. Way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from the European Space Agency's December 15th, 2025 release on XMM-Newton observations, published at phys.org, the JAXA XRISM mission data from their December 8th, 2025 web story, and Martin Cordner's peer-reviewed paper from the Astrophysical journal Letters, submitted August 26th, 2025, and available on arXiv as paper, 2508.18209. These aren't press releases, these are raw mission data and peer-reviewed spectroscopy showing carbon dioxide to water ratios of 7.6 to 1, the highest ever recorded in any comet. Now back to the information. The asteroid terrestrial impact. Last Alert System Telescope, ATLAS for short, captures 4 exposures between 05-1511 and 06-2031 Universal Time. Right ascension 1807, 27.68. Declination -18, 4140.2. A faint dot moving 73.31 arcseconds per hour against the stellar background. Observatory code W68 reports to the Minor Planet Center. By July 2nd, pre-discovery observations start flooding in. Zwicky Transient Facility finds it on June 28th and 29th. More ZTF images from June 14th through 21st. ATLAS pulls archive frames from June 25th back to June 5th. Someone notes the comet passed directly in front of the galactic center's dense star fields. That's why nobody saw it earlier. Too many stars, too much noise. But the orbital solution doesn't lie. Hyperbolic trajectory. Eccentricity greater than 1. Speed at discovery, 137,000 miles per hour. 410 million miles from the sun. This thing isn't stopping, it's just passing through. Lowell Discovery Telescope in Arizona. Canada-France-Hawaii Telescope at Mauna Kea. All show a marginal coma with potential tail elongation. David Jewett and Jane Liu use the Nordic Optical Telescope. Clearly active. Diffuse appearance. Miguel Alarcon's team at the Instituto de Astrofísica de Canarias uses the 2-meter twin telescope at Teide Observatory. Same date. Same result. Active comet. Reddish color. Dust signature. By the time the Minor Planet Center announces the discovery and assigns the designation 3I Atlas on July 2nd, they've collected 122 observations from 31 different observatories. The letter I stands for interstellar. The number 3 means it's the third confirmed visitor after 1 I Oumuamua in 2017 and 2 I Borisov in 2019. The comet also gets the non-periodic designation C/2025N1, but everyone calls it 3I Atlas. The James Webb Space Telescope aims its near-infrared spectrograph at the comet. Heliocentric distance 3.32 astronomical units. The spectral images span 0.6 to 5.3 micrometers. What JWST sees, a carbon dioxide-dominated coma with enhanced outgassing in the sunward direction. Water ice, water vapor, carbon monoxide, carbonyl sulfide, dust. But the ratio is insane. Carbon dioxide to water, 7.6 plus or minus 0.3. That's among the highest ever observed in any comet, 4.5 sigma above the trend for long-period and Jupiter family comets. The only outlier close to it is C/2016 R2. Martin Cordner at NASA's Goddard Space Flight Center and Catholic University of America leads the analysis. The paper goes on arXiv, August 26th. The numbers don't fit. Most comets show abundant water relative to carbon dioxide. 3I Atlas is backwards. The carbon dioxide coma spans at least 348,000 kilometers in radius, visible only in near-infrared. Mid-August observations confirm JWST's findings: high carbon dioxide, low water. The comet is 320 million miles from Earth when SphereX captures its multispectral view. Researchers at Caltech announced the detection August 21st. The composition suggests either an intrinsically carbon dioxide-rich nucleus or a comet that's been cooked. Billions of years in interstellar space. Galactic cosmic rays hitting the surface, converting carbon monoxide to carbon dioxide, synthesizing organic rich crusts. Laboratory experiments show this works. Cosmic ray irradiation efficiently converts CO to CO2. The outer layers get processed. Estimates of 3. I-Atlas's erosion rate indicate current outgassing samples only the processed zone. Depth, 15 to 20 meters. The pristine interior material, never reached, not yet. The comet is depleted in carbon chain compounds. The upper limit to the C2 to CN ratio suggests 3I Atlas is one of the most carbon chain depleted comets ever known. But there's nickel. And there's cyanide. Spectroscopic observations on August 21st detect cyanide emission and nickel in the coma. Lowell Observatory reports the first tentative cyanide detection on August 22nd. The nickel to iron ratio is unusually high. Most solar system comets show nickel and iron together in roughly solar proportions. 3I Atlas shows strong nickel emission but weak iron early on. As the comet approaches the sun, the ratio normalizes. Temperature-dependent release or different chemical pathways? Unknown, but it's a data point. Metal content in interstellar matter, benchmark for future studies. Hubble space. Telescope images from July 21st show a teardrop-shaped cocoon of dust. The comet is 277 million miles from Earth. Hubble tracks the comet moving on its hyperbolic trajectory, so background stars streak in the exposure. Observations through August 20th constrain the nucleus diameter. Upper limit, 3.5 miles. Could be as small as 1,444 feet. The coma measures 26,400 by 24,700 kilometers in diameter, according to the Grand Telescopio Canarias on July 2nd. About twice Earth's diameter. The angular diameter is tiny. July observations measure 2 arcseconds for the most visible part. The coma's full width at half maximum. 10 arcseconds for the full extent. As the comet approaches the sun and becomes more active, the coma grows. Density increases. More gas, more dust, more outgassing. The comet appears as a slightly fuzzy white dot moving downward near the center of the frame. Cassis can't distinguish the nucleus from the coma because 3I Atlas is too far away. Imaging a kilometer-wide nucleus at that distance would be like seeing a mobile phone on the moon from Earth. Impossible. But the coma, a few thousand kilometers across, is clearly visible, created as the comet approaches the sun. Heat and radiation bring it to life. Gas and dust release collect as a halo surrounding the nucleus. The full size can't be measured because brightness decreases quickly with distance from the nucleus. The coma fades into image noise. Mars Express uses its visual monitoring camera with exposure time of just 0.5 seconds, the maximum limit for the spacecraft. The comet doesn't reveal itself in those images, exposure too short. Scientists stack several frames together to try to spot the faint comet. They attempt spectral measurements using Mars Express's Omega and SpyCam spectrometers, and ExoMars Trace Gas Orbiter's Nomad spectrometer, uncertain whether the coma and tail were bright enough for spectral characterization. Analysis continues over the following weeks and months. 1.4 astronomical units, about 130 million miles, just inside the orbit of Mars. The comet's speed at perihelion, 153,000 miles per hour, pulled by the sun's gravity, accelerated from 137,000 at discovery. Non-gravitational forces from outgassing cause small perturbations in the trajectory. Jets of gas and dust escaping the surface act like tiny thrusters, subtle changes. Observations show these perturbations are small and compatible with normal cometary activity. The Unistellar Network, a global community of citizen astronomers coordinated by the SETI Institute, collects near-continuous photometric data, brightness changes, potential outbursts, fragmentation events. Frank Marcius, senior astronomer at SETI and chief science officer at Unistellar, coordinates the effort. Combining observations from citizen science telescopes with major ground-based and space-based observatories, tracking trajectory, measuring composition and behavior as the comet warms. X-ray observatories like XRISM and XMM-Newton need at least 60 degrees separation from the sun. XRISM, pronounced CRISM, is the X-ray imaging and spectroscopy mission, led by the Japan Aerospace Exploration Agency in partnership with NASA and ESA. 2 instruments, Resolve, an X-ray calorimeter capable of measuring individual X-ray photon energies with unprecedented resolution, and Xtend, a large field-of-view soft X-ray CCD camera. The mission plans a target of opportunity observation. Comets are brightest near perihelion, but XRISM's instruments can't point close to the sun. The observation is carefully scheduled for the moment when the comet has moved far enough from the sun to fall within XRISM's allowable pointing window. From 2320 on the 26th to 2038 on the 28th. XRISM conducts observations with effective exposure of 17 hours. The comet drifts slowly across the constellation Virgo. The satellite's attitude adjusts approximately once every 3 hours, 14 times total, to keep the comet near the center of Extend's field of view. Extend's field of view covers a region of about 3 million square kilometers. The X-ray image reveals a faint glow extending roughly 5 arc minutes, corresponding to a distance of 400,000 kilometers, around the cometary nucleus, difficult to explain solely by blur from X-RISM's imaging performance, suggests a diffuse cloud of gas surrounding the comet, faintly glowing in X-rays over several 100,000 kilometers. Similar structures can arise from instrumental effects like vignetting or detector noise, so careful analysis is required, but the spectrum doesn't lie. The observed emission likely arises from charge exchange interactions between cometary gas and the solar wind. When gas molecules streaming from the comet collide with the solar wind, a continuous stream of charged particles releasing from the sun, they produce X-rays. The solar wind ions rip electrons from the gas atoms. Charge exchange. Electrons pushed away with such energy they emit X-rays. Doesn't matter that comets are among the coldest objects in the universe. This plasma interaction produces electrons with temperatures of millions of degrees. Signatures of carbon, nitrogen, and oxygen appear in the data, evidence that cannot be dismissed. X-RISM's findings are released December 3rd as a rapid announcement in the astronomer's telegram. Other teams immediately begin planning follow-up observations. The early data becomes a key foundation guiding subsequent campaigns. XMM-Newton uses its most sensitive X-ray camera, the European Photon Imaging Camera, EPIC-PN. The image shows the comet glowing in low-energy X-rays. Blue marks empty space with very few X-rays. Red highlights the comet's X-ray glow. At the center of the image, a bright red spot stands out against the dark background like a fiery beacon. Faint gradients of purple and blue spread outward, creating a slightly rotated rectangular frame, divided by a thin horizontal line, the detector gap, a black streak from an interior vein in the EPIC instrument itself. A yellow arrow labeled Sun points left, indicating the comet's orientation in the solar system. Attempts were made to observe X-rays from 1I Oumuamua and 2I Borisov. None succeeded, no detectable X-ray emission. Whether interstellar comets behave like ordinary solar system comets or exhibit entirely different characteristics remained a long-standing mystery. 3I Atlas breaks that silence. First interstellar comet observed in X-ray light. The glow comes from solar wind interacting with gases like water vapor, carbon dioxide, or carbon monoxide. Telescopes like JWST and Sphere-X already detected those, but X-ray observations are uniquely sensitive to gases like hydrogen and nitrogen. These are almost invisible to optical and ultraviolet instruments. Hubble can't see them well. ESA's JUICE mission can't detect them. X-ray observations are a powerful tool. They allow scientists to detect and study gases that other instruments can't easily spot. Charge exchange reactions with the solar wind. Evidence is overwhelming. 3I Atlas is producing X-rays, just like solar system comets. But with its own twist, the extent of the glow is immense, 400,000 kilometers from X-RISM, about 250,000 miles. That's roughly the distance from Earth to the Moon, a halo larger than most cometary comas ever observed in X-rays. The gas cloud must be astonishingly sparse and diffuse. The X-RISM team explicitly states they are still working to untangle the full implications. Some of the blurring in the imaging might be instrumental. Vignetting reduces intensity at edges, creates appearance of extension. More rigorous processing is underway to distinguish genuine emission from artifacts, but preliminary results already indicate a signal above expected noise. What does this reveal about 3I Atlas's true nature? Start with the basics. Interstellar object. Third confirmed. Arrived from the direction of the constellation Sagittarius. Trajectory traced back shows it comes from a region of the galaxy older than our solar system. Earth and the Sun formed 4.6 billion years ago. 3I Atlas may have formed around a star 7 billion years old or more, billions of years older than the Sun. Think about that. This comet carries material from another stellar system, another protoplanetary disk, different star, different metallicity, different environment. The parent star of 3I Atlas is unknown, but properties and environment can be inferred from composition and dynamical membership in the galactic disk. If it's a member of the thick disk, the parent star could be a low metallicity star with heavy element abundance at least 40s. Percent of the suns. 3I Atlas is presumed to have formed within a protoplanetary disk of gas and dust surrounding its parent star when the star was young. Observations by JWST and Sphere-X show the comet is rich in carbon dioxide, suggests it formed far from its parent star, beyond the carbon dioxide frost line where temperatures are cold enough for carbon dioxide to condense into solid ice. At some point after formation, 3I Atlas was gravitationally flung out of its parent star system. Close encounter with a giant planet, stellar flyby, ejection velocity exceeded escape velocity. The object began wandering the Milky Way, traveling through interstellar space for billions of years. During that time, galactic cosmic rays bombarded the surface, high-energy particles, protons, heavy nuclei. Cosmic ray irradiation converts carbon monoxide to carbon dioxide, synthesizes organic-rich crusts. Laboratory experiments demonstrate this process. The outer layers of 3I Atlas consist of irradiated material, properties consistent with observed composition. Observed spectral reddening. Estimates of erosion rate indicate current outgassing samples only the galactic cosmic ray processed zone. Depth 15 to 20 meters. The pristine interior material, the original ices from the parent protoplanetary disk, remains locked inside, untouched, at least for now. As the comet continues to sublimate, future outgassing might expose deeper layers, but by then it will be too far from the sun, too faint to observe, gone. Long-period comets from the Oort cloud show carbon dioxide to water ratios around 0.5 to 2. Jupiter family comets from the Kuiper belt show similar ranges. 3I Atlas is 6.1 sigma, above the trend as a function of heliocentric distance. Statistical outlier. The only comet remotely close is C/2016 R2, which also showed extreme carbon dioxide enrichment, but that's a solar system comet. 3. I Atlas comes from outside. Two possible explanations. First, intrinsically carbon dioxide-rich nucleus, formed beyond the carbon dioxide ice line in its parent system. Conditions cold enough that carbon dioxide condensed before water. Second, galactic cosmic ray processing. Billions of years of irradiation converted carbon monoxide to carbon dioxide in the outer layers, suppressed water sublimation. The carbon monoxide to water ratio of 1.65 plus or minus 0.09 supports the second hypothesis. Substantial absolute carbon monoxide levels. Red spectral slopes, organic-rich crust, all consistent with cosmic ray processing. The extent of the X-ray halo, 400,000 kilometers, is unusually large. Charge exchange reactions depend on density of neutral gas in the coma and density of solar wind ions. If the gas is sparse and diffuse, the interaction zone spreads out. Low gas production rate relative to coma size. 3I Atlas is emitting gas, but not at the furious pace of a typical comet at that heliocentric distance. Why? Possibly because the carbon dioxide-rich composition changes the sublimation dynamics. Carbon dioxide sublimates at lower temperatures than water, between about 90 and 200 Kelvin. Water ice requires higher temperatures. If the surface is dominated by carbon dioxide ice with a carbon dioxide-rich crust, heat penetration into the nucleus may be inhibited, suppresses water sublimation rate relative to carbon dioxide and carbon monoxide. The result, lower total gas production, sparser coma, extended X-ray interaction zone. When the full analysis is complete, scientists will compare 3I Atlas's elemental abundances to solar system comets. Are they similar? Different? Do they reflect the metallicity of the parent star? The chemical environment of the parent protoplanetary disk? These questions will take months to answer. The data is complex, requires careful modeling of charge exchange processes, accounting for solar wind conditions, comet gas composition, geometry of the interaction. But the potential payoff is enormous. First direct measurement of elemental abundances in an interstellar comet using X-ray spectroscopy, benchmark for all future studies. But still producing enough gas for detectable X-ray emission. If observations had been attempted earlier, say in September or early October, the comet would have been too close to the sun in the sky. X-ray observatories couldn't point at it safely. If observations had been delayed, say into late December or January 2026, the comet might have been too faint. Gas production drops as heliocentric distance increases, coma thins. X-ray emission fades below detection threshold. The observational window was narrow, November and early December. XRISM and XMM-Newton nailed it, captured the data, made history. On the other side of the sun from Earth, not visible to naked eye. Optimal viewing window passed in November. Those hoping to glimpse it need at least an 8-inch telescope, 20-centimeter aperture. Even then, it's faint. Magnitude around 15th or 16th. The Virtual Telescope Project hosts a live stream. Gianluca Massi, astronomer and astrophysicist at Bellatrix Astronomical Observatory in Italy. Founder and scientific director of the Virtual Telescope Project. Scheduled for 4 a.m. UTC Saturday, 11 p.m. Eastern Time Friday. Cloudy weather delayed the original Thursday night attempt. The live stream gives skywatchers a final chance to see 3I Atlas before it fades. After December, the comet continues outward, away from the sun, away from Earth, speed decreasing as the sun's gravity pulls against its motion, but still on a hyperbolic trajectory. Escape velocity maintained when it crosses the heliopause, the boundary where solar wind pressure balances interstellar medium pressure. It will be traveling at the same speed it entered, roughly 60 kilometers per second relative to the sun, never to return. Perseverance, Mars rover. Mars Reconnaissance Orbiter. Maven, Europa Clipper. Lucy, Psyche, Parker Solar Probe. Punch, Stereo, SOHO. ES emissions, Mars Express. ExoMars Trace Gas Orbiter. JUICE, XMM-Newton. JAXA mission, XRISM. Ground-based observatories, Very Large Telescope. Gemini North, Gemini South. Nordic Optical Telescope. Canada-France-Hawaii Telescope. Lowell Discovery Telescope. Palomar 200-inch, Apache Point Observatory. Academia Astronomical Observatory. Gran Telescopio Canarias. Vera C. Rubin Observatory. Zwicky Transient Facility. MDM Observatory. Teide Observatory. Rosen Observatory. Dozens of facilities. Hundreds of observations. Optical, ultraviolet, infrared, submillimeter, radio, X-ray. Every wavelength tells a story. Every dataset adds a piece to the puzzle. WISPAR instrument, wide field imager for solar probe. Around 10 images per day. Raw, unprocessed observations show the comet moving from right to left. During this period, Parker was speeding away from the sun following its 25th solar flyby on September 30th. The spacecraft's vantage point, inside Earth's orbit closer to the sun, provided a unique perspective, imaging the comet from a different angle. Complementing Earth-based observations, Stereo observed from September 11th through October 2nd, Solar Terrestrial Relations Observatory, designed to study the sun and solar wind, captured the comet in colorized, stacked images. SOHO, Solar and Heliospheric Observatory, captured a glimpse in October, expected to be too faint, but detailed image processing and stacking revealed it. Punch, polarimeter to unify the corona and heliosphere, observed during passage through inner solar system. Combined images show the comet's tail as a short elongation to the right. Maven's ultraviolet instrument imaged hydrogen atoms surrounding the comet. Lucy spacecraft, on its way to Trojan asteroids, spotted 3I Atlas from about 240 million miles away. Psyche spacecraft captured 4 observations over 8 hours on September 8th and 9th. Papers in peer-reviewed journals, press releases from space agencies, social media posts from citizen scientists. The comet becomes a global effort, collaboration at unprecedented scale, because opportunities like this are rare. 1I Oumuamua in 2017, 2I Borisov in 2019, 3I Atlas in 2025, 6 years between the second and third. Who knows when the fourth will arrive? Vera C. Rubin Observatory is now online. Legacy survey of space and time beginning, discovering transients by the thousands, asteroids, comets, supernovae, maybe more interstellar visitors. But for now, 3I Atlas is the prize. Carbon, nitrogen, oxygen signatures, extended halo, confirmed by 2 independent observatories, XRISM and XMM-Newton. New questions. Why is the X-ray halo so extended? Is it because of low gas production, sparse coma, different composition? How do elemental abundances compare to solar system comets? Does the carbon dioxide-rich composition affect charge exchange efficiency? Are there other X-ray features beyond charge exchange signatures? Could there be X-ray emission from the nucleus itself, from energetic processes on the surface? Unlikely, but not impossible. The data analysis continues. Full results will take months, maybe years, but the preliminary findings are already groundbreaking. That light was created when solar wind particles, protons and heavier ions traveling at 400 to 800 kilometers per second, slammed into neutral gas atoms drifting off the comet's surface. The collision stripped electrons from inner shells of the gas atoms, created excited ions. When electrons from higher shells dropped down to fill the vacancies, they released energy, X-ray photons. Those photons traveled through space, crossed millions of kilometers, reached detectors on XRISM and XMM-Newton, got converted to electrical signals, processed by computers, turned into images and spectra. We're looking at the signature of gas from another star system interacting with our sun's wind, alien matter meeting solar matter, creating light we can measure, decode, understand. Carbon dioxide dominance suggests formation beyond the carbon dioxide frost line. Water ice presence indicates the comet wasn't too far out. Carbonyl sulfide, detected by JWST, suggests sulfur in the parent disk. Cyanide and nickel indicate nitrogen and metals. The isotope ratio of carbon-13 to carbon-12 could reveal temperature and radiation environment of the parent protoplanetary disk. The data is partial, obscured, needs more analysis, but it's there. The color change suggests evolving composition as different layers sublimate. Early, organic crust, red. Later, deeper ices, cyanide emission, green. Temporal evolution documented in real time. Large percent of reflected light with oscillations oriented along the Sun-Comet observer plane. Negative polarization is rare, seen in some trans-Neptunian objects. Suggests coma made of mixture of icy and dark material. Particles with specific size distributions and compositions. Modeling polarization requires knowing particle properties, size, shape, composition, refractive index. The measurements constrain these parameters. Provide clues about dust grains, how they form, how they scatter light. Different from typical cometary dust? Maybe. Interstellar origin? Possibly. Or just different formation conditions in the parent disk. The puzzle pieces keep accumulating. Green light from C2 around 516 nanometers. 3-eye atlas shows almost none. Detection limits from VLT and MDM Observatory put upper bounds on C2 to CN ratio. Indicates severe depletion, one of the most carbon chain depleted comets ever. Why? Cosmic ray processing destroys carbon chains, breaks them apart, produces other molecules. If 3. Eye atlas's outer layers were irradiated for billions of years, carbon chains would be gone, replaced by more stable molecules, carbon dioxide, carbon monoxide, organic compounds. The depletion supports the galactic cosmic ray processing hypothesis. Not proof, but consistent. As the comet approached the Sun, the ratio normalized. Temperature-dependent release, maybe nickel-bearing compounds sublimate at lower temperatures than iron-bearing compounds. As the comet heats up, iron emission increases, catches up to nickel. Alternatively, different chemical pathways. Nickel in one molecular form, iron in another, released under different conditions. The data provides a benchmark. Future observations of interstellar comets can check for similar patterns, see if it's a general feature or specific to 3-eye atlas. February. JUICE mission might transmit data from its November 2025 observations. Scientists will analyze. See what the spacecraft saw when it had one of the best views. March. Comet crosses 250 million miles from Earth. Probably below detection threshold for most ground-based telescopes. April. Gone from Earth-based observatories. Still visible to space telescopes if they point carefully. Still producing gas, but weakly. May. 300 million miles. Crossing back through Jupiter's orbital zone, heading outward. June, beyond, into the outer solar system. The realm of Neptune and Pluto. Beyond that, the Kuiper belt. Beyond that, the scattered disk. Beyond that, the Oort cloud. And then interstellar space. 12. By 2040, it will be 100 astronomical units out. Twice the distance of the Kuiper cliff. By 2050, 200 astronomical units, deep in the Oort cloud's inner edge. By 2100, 500 astronomical units. By 2200, 1,000. By then, it will have settled into its final velocity relative to the Sun, traveling through the Milky Way, destination unknown, wandering the galaxy. Maybe in a million years it will pass near another star, feel warmth again, sublimate, glow, develop a coma, a tail, be discovered by alien astronomers who point their instruments and wonder, where did this come from? What star? What disk? Just as we wonder now. Let's build a global community of space enthusiasts who care about the facts. The next interstellar visitor might arrive in a year, in 10 years, in 50. We don't know, but when it does, we'll be ready. Learned from Oumuamua, Borisov, 3-eye atlas. We'll know what to look for, what instruments to use, how quickly to respond. First spectroscopic signatures of carbon, nitrogen, oxygen from an interstellar comet's interaction zone. The data will appear in peer-reviewed papers over the next year. XRISM team papers, XMM-Newton team papers, multi-wavelength synthesis papers, compositional analysis papers, dynamical origin papers, each adding detail, refining understanding, challenging assumptions, maybe confirming some ideas, discarding others. That's the scientific process. Messy, slow, rigorous, self-correcting. The 17-hour observation by XRISM between November 26th and 28th is also archived. The JWST NAIR-SPEC observation from August 6th, the SPHERE-X observations from August 7th through 15th. The Hubble images from July 21st, all preserved, all available, for decades, for centuries. Future astronomers will look back at these observations and see the moment humanity first detected X-rays from an interstellar comet. The moment we prove that objects from other star systems interact with our solar environment in ways we can measure and understand. The galactic center, dense stellar fields, thousands of stars in that region of the galaxy. Tracing the orbit backward through space and time is difficult. Gravitational perturbations from stars, from molecular clouds, from the galactic potential. Over millions or billions of years, the orbit gets scrambled. We can narrow it down to a region, a volume of space, but not a specific star. Not yet. Maybe never. Unless we find another object from the same source. Another comet, another asteroid, with a slightly different trajectory. 2 data points, triangulate. Find the origin, long shot, but possible. If the parent star was metal poor, the protoplanetary disk would have had less carbon, nitrogen, oxygen than the solar nebula. Yet 3I Atlas shows carbon dioxide, carbon monoxide, water, cyanide, nickel. Elements were there, just in different ratios, different ices, different chemistry. The comet is a time capsule, a messenger from the early galaxy, from a stellar system that may no longer exist. The parent star could be dead, evolved into a white dwarf, or a neutron star, or nothing, dispersed. The planetary system, if there ever was one, long gone, scattered, ejected. 3I Atlas is all that remains, a lone wanderer carrying the memory of a place and time we can never visit. Solar wind from our sun, a middle-aged G-type star, colliding with gas from a comet formed around a star that may have been older, cooler, or hotter. Different mass, different composition, different fate. The photons we detect encode that interaction. Wavelengths determined by ionization energies, transition probabilities, quantum mechanics. The same physics everywhere, the same rules, but applied to different materials, different histories. That's what makes the X-ray observation so powerful. It bridges the gap, connects the alien and the familiar, shows us that even visitors from other star systems play by the same rules when they enter our solar system. Yellow arrow pointing to the sun. Scale marker, 5 arc minutes. The image will be in textbooks, presentations, documentaries. It represents a turning point. Before 3I Atlas, theories. After 3I Atlas, data. Interstellar comets emit X-rays, extended halos, charge exchange signatures. The mystery isn't solved, but illuminated, one photon at a time. JAXA leading XRism with NASA and ESO as partners. SA operating XMM-Newton with European contributions. Shared data, shared goals, shared success. The comet doesn't belong to one nation. It belongs to the solar system, the galaxy, the universe, and the data belongs to humanity. By early 2026, X-ray emission will be undetectable, but the data remains archived, analyzed, published, permanent. Future missions will reference it, future researchers will build on it. Meets our solar wind. That story is now part of the record. Verified. True. Shocks. Turbulence. Magnetic reconnection. If confirmed, it means the interaction zone around 3I Atlas is more violent than expected. Not just gentle collisions, but shocks. Fast shocks. Bow shocks where the comet's outflow meets the solar wind head-on, creating regions of enhanced heating, enhanced ionization, producing X-rays at higher energies. The full analysis will take time, more modeling, more comparisons. But if true, it means we're seeing not just charge exchange, but also shock physics, plasma physics, magnetohydrodynamics, at the boundary between an interstellar object and our solar environment, a laboratory we can study from afar, a natural experiment we could never create on Earth. It's not just a comet, it's a probe, a test particle, sampling our solar wind, showing us how it responds, what happens when interstellar matter meets solar matter, what physical processes dominate, what signatures emerge. It's a Rosetta Stone, decoding the interaction, teaching us about both sides, the comet and the wind, the visitor and the host, and in doing so, it shows us a glimpse of the galaxy beyond, the stars beyond, the systems beyond. Out there in the dark, waiting, sending their messengers, one by one, across the light years, into our telescopes, into our data, into our understanding.